Well, we have to hurry along and begin this talk with potentials. I introduced it by saying that it turns out that potentials and potential energies, if you can use them for certain purposes, simplify electrical and gravitational problems considerably, mostly because energy is not a vector. It's a scalar quantity. For example, if you have two energies, you can just add them, and there's no direction involved. Whereas if you have a force, you have to add them vectorially. So that can be a big advantage. Now, the problem is that there are all these definitions and conventions that we have to learn. But I think that, for example, we have some familiarity just with the idea of gravitational potentials. I mean, we don't call it that, but the idea is if you lift something up, you know that you've given it the potential to do some work. That is, it can go down and move something else. So that is a form of energy. We know that, for example, in the gravity potential, things at the same height have the same potential energy. For example, if I want to lift a heavy box and put it on a shelf, the gravity field is acting on the box. And so when I put it up on the shelf, I'm giving the box in the gravity field extra potential energy. So moving it up and down along the field gives it a potential energy. But moving the box sideways on a shelf doesn't take that much force, because I'm not really fighting against gravity. So we get the idea that the gravity affects the potential energy if you're moving for or against it. Whereas if you're moving sideways, it has the same potential energy. I mean, everything at the same height has the same potential energy. In fact, we have a word for that, equipotential. So if you have gravity, the lines of the gravity force are this way, but the potential energy surfaces are this way. That's a force. Let me put down V. V is the symbol for potential. And this will be a characteristic of potentials. This is an equipotential in the gravity field. And there are a series of equipotentials. This could be the top shelf. This could be a different shelf. That's another equipotential. And we would say that this level has a higher potential than this level, right? I mean, it's just higher shelf. And we've lifted it higher. So actually, the field has done more work, negative work, actually, to get it up here. I have to say that we struggle with the idea of who's doing the work. I think I mentioned that earlier. And different, very great experts in the field differ on what they talk. In fact, in your book, Wolfson switches between whether you're doing the work or the field is doing the work. It's a funny thing. That different experts look at it differently. For example, in this case, let's say I have a box, and I lift the box. I put the force on the box to put it on the shelf. Now, what's the gravity field? This is me. This is I. This is I. It is I. Right. Okay. People skip that one. Okay. But the gravity field is force. The force of gravity is that way. So we will take the definition that we're always going to consider what is doing in the field. So I'm going to choose this definition. In other words, if I lift this box upward, the distance that it moves is opposite to that of the gravity field. So the gravity field does negative work. Is the force of gravity times dx. In this case, those are vectors. Again, the work is a scalar, is a number. But the force of gravity times that distance moved, in this case, will be negative, because the gravity is this way and the force is that way. So we would say that the field has done negative work. Whereas if the box falls off the shelf, the gravity field and the direction that it's moving are in the same direction. So if the box falls off the shelf, and it falls at distance dx, and the gravity field is that way, then the work done by the gravity field, you see this is positive, because the gravity field, the vector, is parallel to the dx. So this is a positive work. So we get the strange idea is this one, where the field can do negative work. Or in other words, one way of saying it is we're doing work on the field. So it's very tricky, but I like this way of looking at things because it doesn't take the anthropomorphic feature out of it. It's not that I am doing work. Think just about what the field is undergoing. So we will just stick to this approach, namely, don't worry about what I'm doing, just worry about what's happening to the field. And then I think things work out very nicely. So, and then what we have shown is that the work done is equal to, here's the negative signs, they're kind of funny, the change in the potential energy, but with a minus sign here. And you'll see how that, sticking to this kind of definition, you get the law of conservation of energy comes out, because the work done is equal to the change in the kinetic energy. This again is the analogy of the bobsledders. If he does work, in other words, the bobsledder gets, the guy who's pushes the sled, puts a certain amount of force to a certain amount of distance, which is the work, and he ends up changing the kinetic energy. But look what happens if we define it this way very nicely. These two are equal. K final minus K initial is equal to minus U final minus U initial. With that minus sign. Let me put all the final things on this, final things on one side, initial things on the other. Okay, so I get minus K initial. The U initial is plus, minus and minus makes a plus. I bring it over here, minus U initial equals, and I put K final on the other side here, minus K final. And I have here minus U final. Well, I got a lot of minuses, so I just multiply through by minus, and I get the law of conservation of energy in a potential field. That is that K initial plus U initial equals K final plus U final. By choosing a sign that way, I get this nice statement of the conservation of energy. That is to say, the sum of the kinetic plus the potential energies is a constant in the field, which is what I'm saying here. If I raise this, I give it some potential energy. If I drop it, I lose potential energy, but I've gained kinetic energy while it's falling. So that's a very powerful law. And we just have to be a little admiring of the fact that people figured this out, and so you've got to keep it in your head where do you put the minus signs. You got to get used to this. It's really not easy. So we have this familiar example of gravity. We do it not knowingly, but we do it all the time. Lift things up and see them fall. First thing a child does is pick things up and throw them on the floor. So, now the similar thing is true with the electrical field. Both of them are conservative fields. They both have this fact that they have a potential energy. The fact is that the electric field, for example, we've come across electric fields of the same type as this, where, for example, you can to make a field or a force. Well, to do the electrical case, there's a little different, because here we have a choice of charge. The case of gravity is always attractive. Here's the Earth, and here's an object. The force is always attractive. Now, with electric things, we have the option of two different charges. But okay, let's pick the plus charge for the sake of argument. In which case, the field is for a plane. Then we define the electric field as running away from plus charges. So we have here. But if it's a plane of charge, then again we have a uniform electric field. Again, this is a symmetry property. If you have an infinite plane, there's no reason why the line should point to the right, the left, forward, or back, so they will point vertically upward. Moreover, if it's an infinite plane, and there's no other negative charges there, these lines can't end. So you have the case of a uniform field. In the case of a plus charge like this can also be proved by using Gauss's law, that in the case of an infinite plane. In other words, this is a similar situation, except for the direction of the electric field compared to the gravity field. But here, the electric field is this way. But it's a similar case, and we can define similar things. We can define the potentials in here. In other words, if I'm a plus charge, well, that wouldn't be, yeah. If I'm a plus charge, I think here's where the sign difference comes in and complicates things. If I'm a plus charge, I'm repelled by this plate here. So it's opposite to the gravity field. The force is now this way, whereas the gravity force was downward. We sort of reverse the story. It would take work to push, work by the field. The field is going to do negative work. If I push that electric charge downward toward this plate, the force is that way, the direction is that way. If I push a positive charge down, then my F dot dx, being in opposite directions, will be negative. I'll do negative work. The work is negative. But the change in potential, being the opposite sign, is positive. So I increase my potential by bringing the plus charge toward the plate. That makes sense? The fact is, you see, it doesn't want to be near the plate. But if I push it down, I increase the potential because it wants to spring back. So I've increased the potential of its moving. Whereas if I take it further away, it's used up some of its potential, because that's the way the field wants it to go. That's the kind of feeling I want you to have of this property. Now, this is a definition of potential, and here's actually sort of the mathematics of it. It's still unfortunate that it's a little bit mathematical, but it says what I just said here. Namely, that first we define what we call work, which is a force acting through a distance. And I showed you, I think, last time, that if you have work done, it will produce change in kinetic energy, all things, if those are the only things acting. And in this line here, I define the change in potential from final to initial with a negative sign compared to the work that is done. Now, the work that's done by the field is this Q0, the force is Q times E. And the work done is that force, QE, times the distance through which it moves. So that is the change in the potential, what's called potential energy. That's an energy, because work and energy are the same thing. That's what this line means. Now, the other concept that we have is that of, we have the one idea is potential energy, which is, it's an energy, it's in units of joules, or joules, I guess, better. Joules sounds kind of jolly. So that's an energy, and it's a force times a distance, or it's a half mv squared of units of joules. Now, just as we can actually look at the units here are, it was force times distance as a unit here. The force is given by QE, right, electric force times dx. Now, we can get another quantity of interest by dividing out the Q. So we get du per Q, and that is equal to E dx. So this quantity, that is the energy per charge, is called the voltage. The analogy here is to, when we first defined the action of two charges on each other, we started out saying that first there was a force between them, which was related to Q1 and Q2 over r squared with some proportionality constant. But then we said, no, let's look at it a little bit differently. Let's imagine Q1 here is producing some influence in the field. This is the force of 1 on 2. Let me just figure out, what does the field do to 1? Charge 1 is creating this field out here. And the way we got that, we took the force of 1 and 2, and we divided by Q2. So we got K Q1 over r squared. So we were trying to say, this is an influence due to 1, and then we can put Q2 in that influence. But this is kind of like a free-floating thing that's just there, created by Q1, but we just put Q2 in there, or Q3 or Q4, but whatever it is, Q1 has produced its thing. It's only dependent on Q1 and the distance, and you can put the Q2 any place. So we're doing a similar thing here. We're going to define we have defined the energy as something Q times E, but you see E was produced by somebody else. See, I put this Q in an E field, and I multiply by dx. I can get the per unit energy by dividing through by Q. So I get something which is analogous to this quantity here, something per unit charge. It's the energy per unit charge, which is volts in units is joules per coulomb. But that, the unit volt is used so much that the joules per coulomb is used so much that we give it its own special name, volt. And your batteries come with volts on. You get a 1.5 volt battery, you get a 9 volt battery. In your car, there's a 12 volt battery. It's the energy that any charge coming out of your battery, each unit of charge will have an energy of 12 joules per each coulomb. So we'll get used to that notion pretty soon. Now, there's a lot of stuff here. The only thing that I would do now quickly, if I can, is to find the potential due to a particular charge. Let's say the potential V is just due to the electric field due to some charges times some distance, and you get the voltage, the shelves that it's built on. So now here's one case, the planar situation. The opposite of that, in a way, is a point. See, this is an infinite sheet. Now you can find the potential due to a point charge, just Q. We know it has electric field going out now like this. Now similarly, what we're going to do, we're going to do that thing here. We're going to find the voltage or the potential at some position R by doing that integral, the integral of E times dx between 2 points. So what voltage gives you is the energy difference. Just like if I put something on a shelf over here, it has a certain potential difference between here and the table. There's a difference between this level, height 1, height 2. But on the other hand, that same level with respect to the floor has a different potential because this thing will be moving faster when it hits the floor than it hits the table. So we always measure with respect to a difference when it comes to potential energies. Because there is no absolute value. How much potential energy does it have? Well, it depends where I am. If I'm on the third floor, I have a certain potential energy with respect to the third floor. On the other hand, it's a different potential energy with respect to the second floor. And with respect to the first floor, it's a different potential energy compared to the top of the campanile. So there's always a difference. So you integrate between 2 points, x1 and x2, and you get a difference. And this will give you v2 minus v1. So that's the gist of this derivation, which is in the book. So maybe I shouldn't go through it. If you don't like integrals, this may appall you. But it's a relatively simple integral because you're putting in here the electric field. And the electric field we know is 1 over 4 pi epsilon naught q over r squared times what we're doing is we're going to integrate, what does he do, from r to infinity. So he's going to start at r, and he's going to integrate how much force, or how much is the field as I integrate all the way out. Now the field is changing. E is q, this q here, maybe make a big q, over 4 pi epsilon naught r squared. So as I go out, this field, E, is changing, and I multiply by the element of distance I go through. The field force is acting through that distance, and I keep adding up all those fields and distances from r all the way to infinity. That's what that integral is trying to tell you. And because this is a known integral, the integral of r squared, 1 over r, we'll think of it as r to the minus 2 dr, for those of you who like math, it's equal to r to the minus 1 with a minus sign, integrated between r and infinity. So that's all they're doing there, and you get a 1 over r dependence that you get that the voltage, the potential at a point r is just q, the same q that started it all, over 1 4 pi epsilon naught, but it's now inversely as the distance. And the nice part also is that it's a scalar. So you can, if you have two charges, q, the matrix q1, q2, if q2 has a certain potential at that point, and this one has a potential at that point, you just add them up, and you got your answer, total potential. And it turns out to be nice. And then again, I repeat this yet again, why potential energies are useful is because, again, they are conserved. That is, total kinetic and potential energy starting will be the same when it ends. Yes, ma'am.
On the previous slide,
yes.
Why on the very last line of the equation do they go back to using the lowercase r and not the uppercase r for the line?
That is probably my fault. Because I cribbed these equations from two different places, and some of the people use big R, and some of the people use little r. But what it means is the point that you're integrating to. In other words, you start here and you integrate to infinity. You want to call it r or little r, it's the same. It's just that, yeah, that's a good point. Sorry if it confuses you. Yeah. Oh, yeah, well, one is a variable. In the integral, it's a variable. See, no, see, that's my fault. This should be a variable. It should be the same variable as this. And this is the place I'm starting, and this is the place I'm ending. And this is r, little r is a variable. It should have been consistent. Sorry. No, you're right.